Hi, my name is Daniel Sills, and for the UofL course Applied Robotics 1, we are constructing a submersible robot capable of accomplishing some specific tasks that I'll talk about later on in the series. This is my video check-in 1 for week 2 of the course. So I'll be discussing the design of the robot as well as some of my concerns and things that I'm doing to address those concerns early on through the design process. So here we have a front-on view of the robot design and a top-down view of the robot design, both with selective components chosen not to be drawn to give you some more detail. You can tell that it is a 3-tube design, the central one being the main body of the robot, housing all of the electronic components, and the outer 2 tubes being the ballasts for the robot, allowing it to change its buoyancy through peristaltic pumps pumping water in and out of those ballasts. In the image on the left, you can see the central object that looks kind of like an elephant. Let's see if I can get a... Yeah, here's a laser pointer. All right, hopefully that's coming up. This object is the camera. This would be facing out of the front of the robot. And then this structure that you see kind of wrapping around here, the goal would be to make that a 3D printed structure, allowing this area to be a cavity for placing the batteries for the robot, as well as any weights we might need to adjust that buoyancy. I plan for this section of the robot to be a 4-inch PVC pipe, and then these to be 2-inch PVC pipes. And then I'll discuss how that affects the buoyancy here in a couple slides. Over here you can see a cutout of what we're blowing up right here, so that we can take a deeper look at it. This entire structure is going to be mounted onto the head of a servo motor, allowing the 45-degree thruster direction to be pivoted around that angle, allowing for greater mobility of the robot. It can either be directed out to the left, and then the pair to the left and right would give a great deal of mobility in a neutral axis, or it could be pointed up or down to allow us to kind of tilt the nose of the robot up or down with relation to the thrust. So it's a thrust vectoring system, essentially. The goal is to kind of use a couple PVC components in order to build this into a dry chamber for the motor here, and then use a ducted fan system to produce thrust out of this 45-degree street joint is what it's called. This pipe would have holes drilled through it so that the water would be able to enter through the holes and then out of the duct. The next component that we're going to discuss and provide a little bit more detail on is the pump design. I have purchased 2 peristaltic pumps, but the motor needs to be waterproofed in some way. So the goal here would be to use a PVC end cap with a tube and then another PVC end cap to kind of create a housing for the motor that goes along with the pump, and then the shaft would be able to run through that housing to the pump design. And then the significance of this being a peristaltic pump means that it can provide direct head pressure and sealing to the ballast tanks with a standard, I believe it's called forced induction pump. It would essentially allow, whenever the motor was not running, the ballast tanks to just fill with water as air slowly escapes through the pump. And so that's the significance of moving to a peristaltic pump. All right, so buoyancy. As I mentioned previously, this is one of my major concerns, and so something that I wanted to address in this video. So here we have a little bit of napkin math going over the body volume with relation to the ballast volumes. with a 6-inch, which that's the goal length for this, so this is not to scale, with a 6-inch central body, we have a volume of 75.4, and we have a ballast volume of 37.7, giving us a total volume of 113.1. If we took this as our displacement volume and we wanted this to be neutrally buoyant with a water mass of 16 grams per cubic inch, we would need a total mass, so we would need the entire robot to weigh at least 1,800 grams. Now, we would like it to float sometimes, sink other times, and then be neutrally buoyant when we choose. So going with a safe percentage in the ballast tanks, I think it makes sense for it to be neutrally buoyant with the ballasts half full. So this would give us a adjusted weight of targeting a total robot mass of 1,500 grams. So with those numbers in mind, we then get to start looking at our starting or component weights. So this is what's going to be going into the robot to help offset some of that. I went ahead and measured the 2 drive motors, 2 servo motors, power board, 10,000 milliamp battery, Raspberry Pi, servo control board, camera, and the quick Pi hat. And I came to a total of 481 grams. So subtracting 481 from 1,508, that leaves us a remaining 1,025 grams that we need to offset in order to make it neutrally buoyant. So here's where we have here's where we get to pick apart our napkin math a little bit. So our napkin math ignores the density of the PVC itself, which has a density of 21.3 grams per cubic inch. So PVC on its own will sink, so that acts as a benefit to us. We then add volume from the outrigged components. Those would be the 2 things that I mentioned previously, the pump and the thruster design. So those are definitely going to add air volume that would not be contributing, or that would be negatively impacting and adding volume that we would need to compensate for. There's a potential that they are small enough that the density of their PVC would actually counteract any added air volume that they are adding, but you can't really be for sure on that. And then added mass from the pumps. I do not have the pump motors, but I do know that they are larger in size than my thrust motors, and so theoretically they would additionally be heavier. The goal, I chose 2-inch PVC pipe because that fit the pump motors the best. So they should hopefully take up a large volume of their space, and that should definitely be a net positive towards adding mass to our system. And then added mass from additional structural components / hardware. I talked about some 3D printed componentry and things along those lines that I will definitely be adding in order to tie everything together. So that will have a major impact, as it will add significant weight from screws and bolts, things along those lines. And then any added mass from wiring. Now, my fail-safe plan here, if I cannot manage to get it heavy enough where the ballasts are working efficiently, is I am considering mineral oil cooling the main chamber. What this means is I would fill the main chamber of the robot with mineral oil. Mineral oil is a non-conductive oil, and it is additionally non-compressible. Air is compressible, and so that means that whenever you have a underwater unit like this, you can compress the air inside as water leaks in. Water does not have to leak only out, it can just stay in and be compressed. That's my plan with the peristaltic pumps. And so that means that you could take on water without noticing an outward air leak. With mineral oil, because it is non-compressible, you wouldn't be able to take on water because you could have a mineral oil water barrier that just met and does not mix. And then mineral oil is 0.8 grams per milliliter, making it 0.2 grams per milliliter lighter than water. But that, with our added mass that I mentioned previously, would almost definitely make it submersible, or give us the buoyancy that we would want. Finally, I wanted to go over some components that I ordered. I ordered 2 peristaltic pumps, a motor controller to drive those pumps, as well as a lot of PVC hardware in order to build the thing. So hopefully next week I have some experiments to discuss on how that went. And I'll talk to you then. Peace.